du matériel que j'aime bien prendre des notes.
Oui. Mais tu peux aller là maintenant si tu veux.
Non, en fait.
D'accord, d'accord.
Ils ont un quart d'heure de retard dans toutes les réunions, mais on est à Paris. On peut peut-être attendre encore 2 ou 3 minutes parce que je sais qu'il y a des gens qui ont dit qu'ils viendraient et qui ne sont pas encore là.
Ça dépend si Maurice vient.
Maurice, tu as vu Maurice ce matin?
Non, c'est bon.
Non, mais justement.
Donc on peut commencer.
Non, mais
Non, il y a Eric qui a dit qu'il allait arriver.
Ah oui, Eric. Eric.
Eric, oui.
Alors peut-être qu'Eric, il sait déjà tout ça.
Eric, il doit savoir. Non, pas tout. Non. Il y a deux parties. La première partie, je ne pense pas qu'il est.
On va commencer.
Oui, c'est bon.
We're going to start. Since we have English-speaking only people, I will do the introduction in English. So it's a great pleasure to introduce Daniel Fuster, who is a longtime colleague and friend. He did his PhD thesis in the University of Zaragoza in Spain. Can I pronounce correctly? Zaragoza.
Yes.
In Spain with Guillermo Jauque and Cesar Dopazzo on very interesting issues that have a lot of interest in his work. So then he did a postdoc here in Paris with me, and then he worked with Tim Colonius in California, and he returned here to join the lab. He is famous because he explained why when you tap the beer on the counter, it makes lots of bubbles going up. It was in all the press and TV and the entire world. This has really impressed many people. But he is also famous in science for other things, and he is famous in the lab because he does a lot of beautiful things with basilisk. So that's what he's going to talk about.
Yes. Thank you, Stefan. So he asked me to give a seminar, and as many people use basilisk, I decided to talk about two different things, but that are somehow related, about the errors that we have when we solve for PD equations in basilisk. And in fact, I think what I'm going to explain is something which can be extrapolated to no matter which solver and no matter which method. So this work is done in collaboration with different people. Mustafa, who is doing PhD now with me, Anka, Luca Prubo, who did a PhD that we supervised in collaboration with Anka Belme, and then Yassine and Eric, with who I've been working on the second part of the talk. So as I'm saying, the main interest that I have is to understand what are the source of errors that we introduce in basilisk. So I think I don't have to present basilisk here. It's a code that Stefan Popinet develops and is based on quad-tree structure. And basically we want to solve PD equations on quad-tree or tree grids. So what are the different source of errors that we have? So a first error we can identify is just purely interpolation error. So this is very simple. There is no equation, anything like this. You can imagine this like a number which establishes the gray color. And then we want to represent this solution as best as we can with the minimum grid points. And so what we do is we are going to adapt the grid and to put the grid in those regions where the solution changes. And like this, we are able to represent the solution or the image in this case very accurately, and still we will have some error. It's not because the solution is exact at every grid point, because there we are putting the exact gray color we have at every point, that we can say there is no error. There is an interpolation error that is there, and that if we want to represent the solution, we want to minimize this error with the minimum grid points. But of course, when we solve a PDE, we can add another source of error, which is a consequence of the discretization of the continuum operators. So for example, if we have derivative, we can apply central difference, and then we can say, oh yes, but when we apply central difference, in fact, the error that we introduce here is also an interpolation error. So it's going to behave very similarly to the one we have here, with the difference that now this error is going to propagate depending on the equation we solve. So this equation here only depends on the structure of the solution. Here there is no equation at all. And here we will have an equation that is going to affect how the errors are going to behave. But there is still a third source of error. So when we do numerics. So in principle, it can happen also for single phase flows, but in the case of multi-phase flows, it's very clear. These are the Navier-Stokes equations we want to solve. So basically, these Navier-Stokes equations are applied for every single phase 1 and 2. And basically, when we solve for these equations here, we need to match the conditions across the interface. So we can have jumps of velocity if we have phase change. We will have jumps of pressure if we have surface tension or viscosity. And then there are conditions also on the fluxes. So here we have the flux of pressure is going to jump due to viscosity. And well, we have the jump of tangential stresses. In this case, we are lucky 0. But we never do this numerically. There are very little people that solve for these equations individually in both phases and use these matching conditions at the interface. What we do numerically is to apply what they call the one fluid model, in which we are going to define some kind of fraction, which is going to vary very quickly across a very thin interface. And then we are going to say, okay, we are going to filter everything across this very small length scale delta, along which discontinuities occurs. And then this is going to allow us to define, for example, various properties, which are densities and viscosity, which are not physical at all. They are just properties that vary very quickly between one phase or the other. But when we have density half between both, has no any physical meaning. It's just a way of regularizing the discontinuities. And in fact, if we look very carefully about what this one fluid model does, it introduces terms into the momentum and in this case, the Poisson equation for the pressure. And these source terms appear here because basically the jump conditions are set to 0. So this is very convenient because we can use all the things that have been done for single phase flows because we don't have any discontinuity formally in the solution, and the effect of discontinuity is translated into sources. So here this is like momentum source we have in the velocity equation, and for the Poisson equation we have the divergence of a gradient. So we will see this. In fact, this allows us to put jumps. In this case, this is going to put a jump on the pressure due to surface tension, and this term here is going to put a jump on the pressure due to normal viscous stress. So the nice thing of here is that here I have not applied any discretization. This is just continuum framework, and this applies perfectly for the continuum equations. So the question we can ask is, can we represent accurately jumps with these kind of models? And well, the The thing is that people say that when we do numerics, discontinuity can be represented at best at first order. So of course this poses a lot of questions. If you want to do high order methods with problems with discontinuities, can we do this? This is the big question I'm going to try to answer, because a priori if you have something which is discontinuous, the best thing you can do is put a line, and then you have an error which is first order, and you cannot get rid of that. So, okay, if you have a classical discretization method that introduces second order errors, and then there is a prefactor here that depends on the grid size. Here H is going to denote the grid size, and I have a regularization error that we expect it to be first order. Here there is a prefactor and here is delta. Of course, we can mix them up. So, for example, in the both fluid method, we are going to put delta equal to H, and then we will say, okay, all the errors depend on the grid size. That's true. But the big thing now is which one is going to control. So, of course, if we refine the grid sufficiently enough, this one is going to control because the power law is smaller. The second question, because the grid size at which the one or the other error will control will depend on these prefactors here. So the question is also, can we predict these prefactors? And eventually, if this comes due to regularization and this comes due to discretization, is how can we increase the order of both error sources? So here I just put an example with this is first order, this is second order, but the thing is that once you have an understanding of from where these errors come from, maybe you can propose models which are higher order. So what are the applications of that is, as I say, if you understand, you can propose higher order schemes because maybe you understand now from where these errors come from, and then you can propose solutions for that. You can also propose subgrid models, especially in the case of regularization, but also in the discretization schemes. You can try to put something which happens at the subgrid scale into the physics. And of course, we can develop adaptive refinement strategies because we will know from where the error comes from, and we know that it's there when we have to refine the grid. So I'm going to start talking about discretization errors. As I say, this is part of the PhD of Luca Pruvo that I did in collaboration with Anka. In fact, here the idea is that if you have a PDE equation that here is defined in the continuous framework, so U is the exact solution, and now we are going to discretize everything. So we are going to discretize the source. We are going to get a discretized solution, U tilde, and we are going to discretize also the operator. So the idea, or what we want to understand, is how the error behaves in a given norm. So the error is just the difference between the exact and the numerical solution. And what we can do here is, this is just the interpolation of the exact solution into a grid. And if we do this, basically what we have here, we just subtract and add this interpolation of the exact solution into a grid. And basically we see that this error is going to be always smaller than the interpolation error, plus an error which is the residual between the numerical solution and the interpolation of the exact solution into the grid. So the numerical error is going to be always smaller than this interpolation error that does depend only on the exact solution, and this error here that I call U prime, which is this residual, which depends on everything. It depends on the discretization scheme, the PDE, and of course the solution. So by definition, this interpolation error is very nice because we get rid of the PDE and the discretization. Does not depend on the equation, it does not depend on the numerical method. So it simplifies our life quite a lot. And this U prime, this is very ugly because this depends on the numerical method we use, and we depends also on the PDE equation we solve. And basically, this is the solution of this problem here. where this S prime is just the residual between this S tilde and the discretized operator applied to the exact interpolated solution. So basically, if the interpolated solution is a solution of a discrete operator, this source is 0, and the only thing remaining is, of course, the interpolation error. Otherwise, we have an additional source of error we have to take into account. So let's see how we can model interpolation errors, because interpolation errors are the simplest ones, and they are very nice. And I was very happy of learning the work of Losey and Alucé, because they provide a theory where they see the mesh as a continuum with a density of grid points. So basically, this density of grid points is the ratio between the average grid size and the local grid size. And when you have this continuum, it's an optimization problem. It's how you distribute a given number of points, and this is going to give you both the local error and the global error theoretically. So basically, it's a theory that provides you these prefactors we were talking, and they are going to tell you basically that if you have a second order method, you are going to converge also with an optimal grid at second order, which is very nice. It's something I never thought about, but of course it's true. If you have a second order method, you cannot converge faster than second order if you are traveling through an optimal grid. So and of course, as I say, this only depends on these prefactors here only depends on the structure of the solution and the number of grid points that we target. So Luca basically generalized this or particularized this for octrees and quadtrees, and basically this what allows us is to compute this optimal and also the uniform grid prefactors that we have as a function of a solution. So I just put an example. He created this structure, and basically you just have to call these compute prefactors, and with these compute prefactors here you put the variable you want to predict, and here is the norm, and basically it's going to provide you the values of the prefactors. And this is going to be very useful now, because when we do a numerical experiment, we have a prediction of the optimal grid evolution. Basically, we measure the error as a function of the number of grid points and the uniform grid evolution. So it's not because we are below uniform that we can say adaptivity works. Of course, it works, but the question is how far we are from the optimal behavior we can reach. So the thing is that when we use adaptive grids, when we try to minimize this interpolation error, are we close to the optimal grids or not? And the answer is that, for example, problem A, yes, we are kind of close, but there are 4 other problems, like problem B, where we are quite far. Here is the optimal curve, here is the uniform grid, and we can see that, okay, we get a little bit better, but we are quite far from the optimal behavior predicted by the theory. So why we are far? We are far because, as we say, this theory just assumes that we are going to reduce the interpolation error. And in numerics, there is this additional source of error that is there, and we have to understand how it behaves. So in fact, this source of error is just as I say, the operator, the discrete operator applied to this variable. It's a problem we have to solve. And on the right-hand side, we have a source. And this source, for example, this is the Helmholtz equation. In fact, this source is going to be this diffusion coefficient, and then the difference between the exact Laplacian of the exact solution and the discrete Laplacian of the interpolated solution. So you can see here that if the interpolated solution is exact, in the sense that it gives the exact Laplacian, this source is going to be 0, this U prime is going to be 0, and basically what means is that you interpolate the exact solution, is also a solution of your discrete problem, and so the only error you have is the interpolation error. Otherwise, this source is not zero, and you have to account for it. So, okay, now you have to get into the numerics and you have to get into the equation. So for this particular equation, this term can be written like this. So this is not the discrete solution, it's the exact solution of the problem. And basically what you see here is that this source is the fourth derivative of the exact solution times the local grid size square. And as I say, it acts as a source. So the source is local, but not the error, because the error is going to be propagate according to the equation. The source is proportional to the grid size square, and it has the structure of a Laplacian. So what is interesting here is that if we now do the structure of the source, so this is for uniform grids. I forgot to say, in fact, there is a lot of error cancellation for uniform grids, and this is how you get this. If you do it for adaptive grids, in fact, you start getting the difference of grid size between neighboring cells. So you have a source that now depends only on the second derivative of the exact solution, and now depends on the gradient of on the changes of grid size in neighboring cells. So basically, if we come back to this vision of seeing the grid as a density of points, in fact, this source depends on the second derivative of the density of points we have. So we can see that, okay, the method converges with h squared, so it's still second order. This error does not behave differently. It's going to be a second order error, just like our initial method. But this error now, u prime, which is very ugly, is going to be even more and more important as the grid size change. So when there are regions of large change of level of refinement. And in this case, the interpolation error is not going to be representative of the exact error. So only when we have this quantity small, so when the level of refinement changes very smoothly, we can more likely to say that the error is purely local. Otherwise, it's going to be more and more problematic. So let's do this. Let's take the problem B, that was the problematic one, and start with a uniform grid. So we start with a uniform grid. We start here, and we are going to start assuming that the error is purely interpolation error, and we are going to refine the grid according to this. So basically what we see is that we get closer to the optimal grid, and just when we touch the optimal grid, puff, it does not work anymore. So we still try to minimize the interpolation error, but then minimizing the interpolation error is a complete disaster, and we make the error explode. So this is good news and bad news. It's good news because in this region, things were working very nicely, and as I say, why? Because here the density of variation of grid size is 0. So here we are having grids where the level of refinement does not change much. And as we get to the left, we are having grids which effectively decrease the interpolation error, but effectively increase the total error. So this is what we do here. We compute the interpolation error just by injecting the exact solution into the grid, and we verify that, okay, when we do these experiments, we follow the optimal curve. There is no issue. And here is the numerical error. This is what we are really interested. And we see that systematically, no matter what is the level of refinement at which we start, we get closer to the optimal grid, and then we explode. Puff, 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 puff. And it has a similar behavior. It always happens the same thing. So what is the difference between this grid and this grid? In fact, in this grid, we have a constraint on the minimum grid size. And in this grid, we don't have a constraint on the minimum grid size. So basically, when we move here to the left, here we forget about what is the minimum grid size we have imposed here, because we are constraining so much the grid that no matter what is the minimum grid size we impose here. So in fact, when we are getting all these points, they are not affected by the minimum grid size. These points that are close to optimal, they are affected by the minimum grid size. So of course, if you have to decide for a given number of grid points which grid you want, you want this one and not this one. And this is basically what we see here. This is the unconstrained grid, and we see this is the total error map. We see a lot of errors, not in the region where the discontinuity occurs, but in the region where we are coursing in the grid. Basically, we see here a lot of errors. And in this other grid, the region is a little bit thicker. We increase a little 1% the interpolation error, but we are reducing by 95% the total error we introduce in the numerical solution. So, okay, the solution is how to restrict the minimum grid size. So the nice thing now is that we have a better understanding. We know that this is the uniform error convergence curve. We know that theoretically this is the optimal convergence curve. And we know that there is almost a straight trajectory between these two curves that exist. So if we do this assumption that there is this trajectory where the uniform error is equal to the optimal error, we can get the intersection, and the intersection point here. In the intersection point here give us the minimum grid size. It's just the average grid size that we want to impose in the simulation, multiplied by the square root of this ratio of prefactors, which can be both evaluated theoretically. So basically, this is what we did in the PSD of Luca. We saw that this is the unconstrained grid, and by imposing the constraint in the minimum grid size, we managed to go down to the optimal grid and decrease the errors by almost, or even more than one order of magnitude. Yes. H-min is the max level, because H-min is just the minimum grid size. Yes, this is a way just to impose the max level that you have to impose in a Basili simulation. And what is nice, it just depends on the solution. It does not depend on the equation. It just depends on the solution. So in fact, you could apply it to other problems. It should all work for no matter which equation you have and no matter which problem you have. Of course, the theory is based on second order interpolation errors. If you have high order methods, then you have to talk to Anka to see how to do this, not to me. As I say, there is other errors, which I call regularization errors. And these errors are important because let's do this very simple example. We solve for the Poisson equation, where is 1 in one phase, 0 in the other phase, and we have a jump on the diffusion coefficients. No jump of the variables, no jump on the variable, no jump on the flux. The solution is very smooth. This is the structure of the solution. If we do a convergence test, we see first order convergence. This is, I was shocked. I mean, this is second order solver, and we only observe first order convergence. This has nothing to do with discretization. For me, this is something else. This couldn't, I mean, this is, the solution is smooth, everything is nice. Why we observe first order convergence here? In fact, this problem, well, here is just even a simpler problem. This is a problem where here you can imagine this wall. This is 1D problem. Temperature is 0. Here temperature is 1. An interface is here at the middle. And again, we have continuity of everything. But of course, we have a breakup of slopes here because the diffusivity is different. The flux is constant, but the derivative is not constant. So what happens is that this problem, we can solve it analytically. And what we see here is the analytical solution for different regularization size of this problem. And finally, what we see is that this is the discontinuous solution. We have a breakup on the derivative. And of course, the regularized problem just defines some fictitious derivative there to match both solutions. What is interesting is that both theoretically and numerically, we have a structure of the error which is first order and that is self-similar. So in fact, if we divide this error by the regularization thickness and we plot it as a function of the domain, we see that we systematically get the same error for different grid size. The error function is always the same. And this error function is quite funny. It increases, it's 0 at the borders because I impose Dirichlet boundary conditions, so the solution there is exact. It increases, and then puff, it jumps, it drops, and then it goes to 0 again. Okay, let's go into more complicated problems, because we say, okay, yes, ready for problem without jumps, it doesn't work very well, it's just first order. What happens when we have jumps? As I say, this is a typical model. Here I put a jump on F and not a, sorry, this should be the flux. It's a mistake. A typical way to regularize this, this should be the jump of the flux.
Oh, okay.
This is the jump of the variable, this should be the jump of the flux. Yes, which in this case I put to 0, but in general, even if I don't put it to 0, when we saw this one fluid model, this is a model that is typically used to replace these jump conditions with something which is continuous. So here is the divergence of this jump multiplied by d tilde multiplied by the gradient of f, and f is something that changes very quickly over delta, and this is lost, but here is the gradient of f, and this is the jump of the flux. So the thing is, does it work? People use it, so you could say yes. So this is an example of a discontinuous solution. Here is with the purple thing, and this is the theoretical, the exact solution of this problem, where we are regularizing the jump over a length. So we can say, okay, it does quite a good job. Here we have a small error. Of course, here it does whatever he can. As I say, the best you can do is a straight line between this thickness delta over which the transition occurs, and then we have a constant like in the original problem. So the nice thing of this red solution, green solution, is that it's continuous, so we can solve it numerically without much effort. So this is what I do here. I focus into the discontinuity, and then I fix this regularization length, and then I refine the grid, and then of course I get more and more points in this region where the discontinuity occurs. So that's good. At the same time, it's very surprising because you can see, you see, this is the regularized analytical solution, which is non-numerics. This is just the solution of the analytical problem. This is the orange one. The one we want is the dash line, which is the solution of the sharp solution with the discontinuity. And then even if we coarse the grid a lot, basically the blue point is here and here. There is no blue point in the middle. We get always closer to the regularized analytical solution rather than to the sharp solution. So even if we don't put numerics inside, the numerics see that there is a regularization length there that acts as a filter. And of course, here inside this region, everything is spurious, especially derivatives. I mean, here the derivative is 0, here is something, and here the derivative is something else. It's nothing to do with physics. And this is a little bit what I say. If we put a cut, if we put a coarse grid, basically we have this grid point jumping from here to here, and they are closer to the regularized analytical solution rather than to the original discontinuous solution we want to solve. So I think this problem of regularization is completely unavoidable when we're representing a solution into a grid, especially when there are discontinuities. And discontinuities, you can see, you can think about this as you wish. This is the primary variable, but you can think into this about the derivative or whatever you want. So it's always the same. So the main thing now is how this error behaves. The error is defined like the solution between the original discontinuous problem and the numerical or the regularized problem. And more importantly, is the filtering irreversible or not? In the sense that if I have this orange line, am I able to recover that solution, or is something which is completely destroyed? Once I have filtered the solution, everything is lost. Well, in this, you can see already here, I can do this for different grid size. The error is going to behave like this. So in fact, these are the error curve for two different regularization lengths. In fact, you see that the error does not converge. The error stays constant because, of course, this error is just the difference between this point and this point. And this does not depend on how small you put the regularization length. This stays constant. So you have an error that does not converge at all when we have discontinuities. So let's model this error. To model this error, this is the original problem we want to solve with jumps on everything. And this is the problem we want to solve. We can solve, let's say, numerically. And when we do this, what we do is, as I say, I remove completely all the discontinuities, and I put some source terms here that account for that. And of course, I also need some kind of averaging procedure where I define the mean diffusivity as a function of the fraction f and the diffusivities of the pure fluids. So the big question is how accurate these models that we put here are to reproduce this original problem, and which average is better to again reproduce this original problem. So in fact, this is the original problem we have. This is the error. These are the jump conditions. Up. This is the problem we want to solve, because this is the problem we know how to solve numerically. So if we make the subtraction, this is the equation for the error. And that was for me quite shocking too, because in fact this is this problem for the error. It has here a source, and the source is just the difference between these two sources that we put here. And then there is a coefficient here that becomes 0 in the outer regions. And then there is a jump conditions for the error. But the problem is closed. So you can solve for this problem in principle. There is nothing that prevents you once you have, and well, more importantly, this problem here depends on the regularized problem. So if I solve the regularized problem, then I can solve for the error problem, and then I can reconstruct the sharp solution. There is no limitation above it. So the answer to my first question, is the filtering process reversible? The answer is yes. We can always solve for the error problem and come back to the original sharp solution. So as I say, once this regularization law and the source term is imposed, of course, the regularized solution is given. And once the regularized solution is given, we can solve for the error problem. And once we have solved for both the regularized problem and the error, the exact discontinuous solution can be recovered. So very happy, the inverse problem is closed. The only question is how to solve it. So to solve it, we are going to realize about the fact that in fact the outer problem is everything that happens outside the regularization region. In this region, everything is very simple, because basically the source is equal to the original source, and the regularized coefficient is equal to the exact coefficient. So basically the equation for the error is just trivial. It's just a Laplace equation for the error. But this equation for the error, in fact, will need to match what happens in both domains. So here I have fluid 1, here I have fluid 2, and I have a small layer here where the error is going to transit, and then I'm going to define a kind of effective jump condition, which is just the difference between the error between this point and this point. And this is going to act as an effective error jump, and following the same logic, there will be also an interfacial error flux source. So basically, for the outer problem, the error jump will depend on the difference between the error between this point and this point, and for the outer problem, the difference on the flux of error depends on the difference of the inner error problem between this point and this point. So now all the difficulty is how to solve the equations in this very thin layer. So this is the inner problem. The inner problem is how we solve for these equations across this very thin layer. And in this inner problem, we have everything. We have a source, we have a jump on the derivatives, and these jumps are now placed on the position of the exact interface. From the point of the outer problem, the jumps were here. Now the jump is really at the position where the interface is located. So let's solve for this order by order, because solve everything at once is impossible. So in fact, there is always, or there is already terms that are 1 over delta. 1 over delta terms, well, depends on the model, but if we have a model like this, basically here, this is 1 over delta. If we apply the divergence to it, we will have 1 over delta square. And basically, when we integrate it, we can see that we have a flux across this region where the discontinuity occurs that depends on this jump and the regularization jump. And then the solution basically is a linear function of f. F is the parameter that we use to transit from one phase to the other. So basically it's a constant minus the jump multiplied by f. It's a linear function. So when we solve for the error problem, these are the effective outer conditions for the error. So they are 0. Very nice. We don't have error that diverge. And this is the structure of the inner error. In fact, the inner error are 1 over delta term does not diverge. It's okay. As we saw, it's an error that stays constant, but it does not diverge. But of course, the derivative diverges. So basically, this variable here represents the error on the derivative. And the error on the derivative represents, is function of the jump of the variable on the original problem. So the error in the derivative diverges, but this is only happens in the regularization region. And of course, nobody is going to come here to measure the derivative in something which jumps. Everybody will say, this is crazy. You don't have to do this. But I forgot. This goes with the sign. So in fact, because I have the error that I introduced in the derivative, I can come back to the real value of the derivative in the regularization region. I just have to do the subtraction. So at order 0, or at order 1, I don't know how you call it, no, order 0, we repeat the same thing. Here we have more things going on. Basically, the inner error depends on the jump, but then we have the errors on the derivative, which depends on the jump of the variable, depends on the flux, and depend on the source of flux that we have across the interface. But still, very interesting, the outer problem is not influenced by all these errors. So the outer problem is happy. And in fact, if you use this model, that is the model we were using in the one fluid approach, the outer solution will be always right. So this will be the structure of the inner errors, but they will be errors that will be confined only within the regularization regions. And we have 3 contributions that are linear contributions coming from the fact that you have jumps on the variable, on the flux, or on the coefficients d. So as I say, because I have the structure of the errors, I can reconstruct the exact solution. This is the exact solution. It's going to be my regularized solution plus this jump plus a term of order delta. And I can reconstruct also derivatives within the regularization region. And this is going to be the analytical form that this derivative takes within the region. So you have something spurious that is this and this. Does not mean anything physically, but if you apply these formulas, you can come back to something which has physical meaning. Basically, we correct the solution to obtain physically meaningful quantities within regularization region. What does it mean? It means that if we have this solution, here I put it for 2 different regularization sites, these are the solutions. If I apply these formulas, which are purely local, I get this solution. So there is no PDE anything to solve. This is just, you evaluate the flux, and then you put it, and then you reconstruct the solution that you have with the discontinuity. You can go further. You can go to order delta, and everything starts to get complicated. Here at order delta, you start having errors that go in outside. So in fact, you have a jump of error and a jump on the flux of error that is going to diffuse outside, and that is going to weigh to this Laplace equation. So things start getting very, very complicated. Here it depends on the flux, on the jumps, and on these functions that I didn't write, that depends on the regularization laws we use. So basically what this means is that, okay, you can use one regularization law or the other. You are going to cancel some terms when we use, for example, arithmetic mean or harmonic mean, but it will never be a universal optimal response, because these prefactors depend on the problem itself. So whether I have to minimize F1, F2, F3, or F4, it will depend always on the problem. So you cannot say, oh, unless, and okay, this is still another thing, but unless you manage to make them all to 0 and to cancel exactly order delta terms, which is not simple, believe me, but maybe possible, you cannot decide which average is going to be better for a general case. It will always be problem dependent. And if we want to get these errors, we have to solve a PDE with these jump conditions to predict these errors. There is no solution for that. So, okay, depends on the structure, no optimal, and yes. So if we come back to this original problem where the discontinuity was occurring, this is the structure around the discontinuity with for two different grid size for the original regularized problem. This is the local reconstruction, just to get order delta terms. And then if I solve the problem at order delta, and then I get second order accurate solution, which is basically perfect. It captures the structure perfectly. So this you can see as a proof that, okay, a problem with discontinuity, you can do it at second order by solving separately the diffuse problem where everything is regularized, and then a problem for the error that corrects for the errors at first, second order, third order.
The three figures on the right.
Here is the original regularized solution. Okay. Here I just apply the local reconstruction to remove the order 1 errors, and this is the solution of this problem. And then basically I correct this. Here you still have delta terms, errors that we propagate outside. So I solve for this problem now everywhere, and then I compensate for this, and then I get the reconstruction, because the problem for the error is with the sign. This is very important. It's not like in the work with Anka, we took the norm. So you lose the sign, you don't know how errors cancel out. Here you really correct exactly for the errors you introduce. And the nice thing of this approach, it gets a mess, but you can do it to arbitrary order. You just do it whatever you want. So in the work with Yassin, I don't have time to explain, so you believe me. We saw that it's possible to predict the error very accurately for different problems with increasing level of complexity. So basically, this is the 1D problem I mentioned. This is a problem of 2D heat advection with a sinus, where there is an interface here at the middle. And we did also this problem with an ellipsoid. Very important, we did all this analytically. There is no numerics here. We just prove that analytically, when you solve a regularized problem, you can get the prediction of the error exact. And now what we submitted recently with Eric was the previous work was without jumps. What we did now is to generalize this to take into account the presence of jumps. So I'm going to show you just one example. This is the example I told you. We have two different fluids. We have here a sinus, and here we have temperature 0. And basically, this is the solution of the original discontinuous problem. There is a discontinuity here of the solution. And this is the solution you get when you regularize with a very thick grid size. So basically, it's 0.1, it's something like this. And you can see here that all the discontinuity is broken. and okay, the solution looks very ugly. I just apply the reconstruction, and when I apply reconstruction, I get something which looks much better, and then I can measure the errors. So basically, always the same numerical solution. In both three cases, I always start from the simulation I will get from Basilisk, but then I put my ingredients to predict the error, and then I can see how the error, you can decrease it to second order, or you can even decrease it to third order. Third order is crazy, but it's possible. You can get third order, and you could get fourth order. The only problem of this is that the expressions get more and more complicated, and to do general is quite a mess, but there is no technical reason why you cannot get fifth order convergence for that. And of course, I repeat again, this is purely theoretical. There is no numerics here, because whenever you have numerics, at some point the discretization errors I was mentioning at the beginning of the talk will take over, and you will not see this convergence rate anymore. So any errors introduced by any regularization method of analytic solution is the presence of discontinuities is presented. First order errors eventually control the numerical, in fact, this is not even true. You can even get 1/delta errors that can control the numerical errors that you get within the regularization region. But okay, if you think about what happens outside the interface, then you always have first order errors that are there. Then whether you see them or not, this is another thing, but they are there, believe me. This error introduces a source of error flags across an interface and an error discontinuity across an interface. And then what we have presented is a simplified arbitrary order correction method to suppress for these errors. And this gives you an optimal choice of the averaging rule depending on the problem. And this is the first step towards the error prediction models, high order regularization models, and efficient adaptivity for multi-phase flows. And just to conclude, some of the work that I'm doing now, in fact, is how to do this numerically, because as I say, we can do it analytically. The thing now is how to do it numerically, and this has some challenge, but okay, I think they will be eventually solved. To develop high order schemes that are implicit, because as I say, these methods, it can be applied to no matter which source. So you can now try to play with the source so that I get directly second order or third order convergence without the need of correcting the errors afterwards. And then with Mustafa, what we are doing is to see the effect of these errors on the development of instabilities. And in fact, it's very interesting here. We just see a Rayleigh-Taylor instability at infinite Reynolds number and with a very thick. Basically, this acts as a filtering, and this theory, I think, can be used also to determine what a DNS for multi-phase flow is in terms of interfacial instabilities. So the thing is how much you have to refine the grid if you want the instability of the flow to be controlled by physical mechanisms and not by these errors that I'm mentioning. And okay, Mustafa will show you soon, I hope, that the behavior of the instabilities when these errors are controlled by the numerics and not by the physics. So that is something which is bothersome. But of course, if you know under which conditions this occurs, you can refine the grid and to make sure that the instabilities are controlled by physical mechanisms and not numerics. So that's everything. Thank you. And questions? No, I'm saying that there are conditions on which these errors control the instabilities. Not always. Don't think that whenever you do a Basilisk simulation, everything is controlled by these errors. I'm saying that these errors can control the development of instabilities.
That's the issue.
This is infinite Reynolds. Yeah. So this is a singular case because the dispersion relation gives infinite growth rate at small wavelengths. So the question we wanted to ask ourselves here is what happens when we do numerics? Because when we do numerics, we do up to the level of the grid size. So are we capturing the right behavior until the level of the grid size? Or is something which is completely wrong? Or is something which makes sense? So this is, but okay, this is Mustafa's the topic.
Then when you have an underslope solver, you solve the problem for pressure, actually a tempo problem. Right? So everything you showed in previous papers could be applied directly to the pressure, or you have to take into account some.
Yes. The only thing here. Here is, yes, these are the equations you have. So, in principle, what I did is to solve this for pressure. So you might think you can apply it straight away, with the difference that, okay, you are solving also for velocity. So in fact, you have now two errors. You have error for velocity, error for pressure, that are going to interact with each other. So when I write an equation for errors, now I will have a system of equations for errors. I will have an equation for the error evolution that will depend on the error on the pressure, and an equation for the pressure that will depend on the error on the velocities. And here you have velocities, you have derivatives of the velocity, so the errors on the velocities act here very strongly, in fact. So I have not looked into that. It's something I will do at some point, because for now I was focusing in, let's say, I assume that this is known, and then I'm interested in knowing what are the errors that I introduce in this equation when this is known. But whenever this is not known given by this, you have to do it. But there is no any difficulty. And this is not your question, but I say that even if in single phase flows, you could think about, for example, turbulence model. You do exactly the same thing. You have a thing, and then you are modeling discontinuities, so for example, fluctuations, and then you could use this to try to see what are the effects of this modeling into the solution. Okay.
Some advice to people who do that with simulations every day, and whether they should use the harmonic mean or the arithmetic mean for viscosity and density.
No. The answer of this is that it depends on the problem. So you cannot give a final answer.
Go back to the slide where you said it depends on the problem.
Yes. Well, yes, here. So basically, what you want, this is the outer solution. So you forget about what happens within the regularization region, and you say, okay, the only thing I care is what happens outside the interface. Very good. Basically, the error jump and the error flux jump is going to control the amount of error you have in the outer solution. So it's going to depend on how much flux you have across the interface, how much the surface Laplacian is, how much this jump is. This is the surface Laplacian of the jump. This is the jump, and this is the flux jump. So when you put numbers here, specific numbers, you can say, okay, I'm going to try to reduce this function or this function or this function or this function. Or if you say, okay, I have a specific problem, I want to minimize this other quantity, and this is something we would like to do with Anka in the future maybe, is to say, okay, I have a quantity of interest, and now what is the law of d tilde that minimize this error? This is something but will always depend on this. This depends on the problem. This is not something you can play with. If you have a problem, for example, one example I was putting, imagine a problem with a jump. This is 0, this is 0. 1D problem, this is 0, this is 0. The only thing which is left is this in one-dimensional problems. So basically this function here is 0 for the harmonic mean. So if you have a one-dimensional problem, use harmonic mean, because the harmonic mean gives you second order. In fact, it can be proven it gives you arbitrary order right away. So use harmonic mean. But if you take this one-dimensional problem and then you say, okay, because in 1D the best is harmonic mean, I'm going to use harmonic mean to no matter which problem, you will make this function 0, which is also here, but you will have these other functions which are not 0, but are quite large. So in fact, I saw a lot of examples where this harmonic mean is not optimal at all. Is much worse than the arithmetic mean. So you cannot give an answer. It will always depend on the problem you are looking at, that the optimal averaging rule will depend.
Yeah, I see the equation. So I have an answer. When you deal with numerics and you have these kind of systems where you have a discontinuity, you have a single cell, which is the one you are doing the regularization.
Yes.
How hard is to converge regarding the linear solver? I mean, are you using multi-bit?
No, wait. Here, and this is very interesting, here there are two things. For now, everything I saw is purely analytical. Yeah. So I solved for this analytically, I don't have any issue to deal with discontinuity. If you want to do it numerically, is more tricky. What you have to do, in fact, is like a egg and chicken. You have a problem with discontinuity. So to solve for the error problem, you have to regularize the error problem. And then when you regularize for the error problem, you introduce errors that you can correct. It's all when you want to do this numerically, it's more. And then what is also very important to understand is that this applies for the continuum limit. So in fact, what I saw is that especially when you refine the grids, if you want to remove small errors, it's better to put a lot of grid points on the interface, or to do thick, because you are closer to this theory. This theory is purely continuous. Here there is no discretization at all. So if you want to get really close to this, even though I say, even if you put one grid point, it works, it's true. It works better and better as you put more and more grid points across this diffuse layer. So this, when I do this numerically, it's quite funny. When I refine the grid, at some point I see discretization errors. So if I want to get rid of discretization errors, I have to put more grid points into this diffuse layer to even improve further the solution, which might look crazy, but in fact it works quite nicely. So as you refine the grid, you even put more points into the discontinuity to capture well the smooth transition between the two regions. And this only allows you for this theory to work. And once you have this theory working fine, you reduce the error nicely to the order you want. Otherwise, you live with first order errors. You can say, okay, I just put one grid size, I see one first order convergence, but I'm happy with this. Okay, fine. But precisely and this is what I saw here is that if you work at this resolution, you have how many orders of magnitude? 6 orders of magnitude reduction of the error. So you will never reach with first order. If I get closer to this, to the theory that allows me to reach to this point, I get much accurate solutions. So it's really useful to put points. I know that it's a little bit counterintuitive, but it's true. But you have to correct. If you don't correct, of course it's bad to put points at the interface.
Okay.
If you don't correct the solution, it's always bad to put points at the diffuse interface, because the errors depend on delta. So basically, if you put more points, it's bad. It will always depend on delta. It will not depend on the number of points you put. If you correct, then it's nice to put points there, because I need my continuum theory to be true and not to be influenced by discretization errors. So I need the transition, I need it to be well represented by the theory. If the transition is worse and worse represented by the theory, my correction method works less and less good. So this will work for infinite number of grid points inside the diffuse layer.
Thank you for the nice presentation. And I have 2 questions about the regularization errors. I like this elegant theoretical analysis. I am wondering, if this analysis and the correction algorithm is related to the fact that you are analyzing a linear PDE.
No, I already thought about this. Linearity makes things much simpler,
Yeah.
but you can apply it to nonlinear PDEs. I mean, nonlinear equations, you can linearize them. So, and then the only thing is that, okay, if you put nonlinear terms, you will have errors that are going to behave nonlinearly, and then the system of equations you have is like in the original. But no, I already wrote some notes. Nothing prevents you to apply this to nonlinear system.
I think you have answered my second question. My second question is that if you want to take into account the advection term, if this
No problem. The only thing of advections, however, is that I didn't talk about errors evolving in time. And then if you want to do the full problem which evolves in time, you have errors that, I mean, it's all a mess to see how the errors evolve with time. But okay, in principle, you can do it.
Find out what people use typically in Basilisk for the viscosity, they use arithmetic mean or harmonic mean. I thought that everybody was using the arithmetic mean, and recently I discovered that's not the case.
No.
Many people now use the arithmetic mean. And so I don't know, do you have any idea of the history of that? How did people begin to use the harmonic mean?
I mean, you say in your book that if you want to solve for this parallel flow, then you should use so maybe you know the history better than I do. Yes. No, but okay. One thing that is true that I mean, this is something I thought at the beginning. And this is something they asked me in the conference, is that okay, maybe some averaging satisfy, because some people were really concerned. Okay, you have to do this average because there is arithmetic harmonic, but then there are many others. And then they say, okay, you use this and it will be perfect. And I show you an example. Look, it's wonderful. And basically here what says is that all this is crap. You cannot say this averaging rule is the best. Now the thing is that, okay, if you use one, are you going to trigger, for example, physical instabilities when you are not resolving all the length scales? Basically this, what tells you is that if you really refine the grid a lot, it should not depend on the averaging rule you use, at least the arithmetic or harmonic. But if you don't, then if you don't resolve all the length scales and then you couple everything with discretization errors and everything, then it's a little bit the work of Mustafa. Maybe it depends a little bit, the growth rates that you observe depend on the regularization law, and then it's better to use one or the other. But I don't know, Mustafa is there, but we didn't observe things like this, but we didn't look much into the detail either about the effect of averaging on the instabilities. But, but yeah, for some reason we always use arithmetic. Yeah. But maybe we use harmonic, we will see that it's more unstable or something. Arithmetic for both. But we do this because analytically it's much easier to manipulate, I think, no?
The first paper we submitted to JCP in 1996 or a very long time ago, we said that we didn't know which was the best mean for the density, that sometimes we got better results with this mean or that mean, and was very worried that the paper would be rejected because we didn't know what we were doing. And the reviewer said, "Oh yes, of course, the same thing happened to me." So maybe now if you want to review it now.